I do not know if I will write even a single equation today, although physical chemistry is expected to have equations. So we'll just chat. And I do not know smart words, like I'm just splitting inside myself. Maybe the right word is dichotomy. Uh, so on one hand, I really want to add practical components so that we learn by doing, like, and Crystal should know correct chem educational words, outcome-based education, right? So on one hand, I'm dreaming about a little project that we all are doing. Uh, so, so how should I pronounce your name? Sophie. Okay, yeah. Nice seeing you, Sophie. Nice meeting you too. So, if we could do a little oh, okay. How should I pronounce your name? Ichu. Ichu. Yeah. Hello, Ichu. If you can do a little project and maybe give a great credit for the project and make it even a replacement of an exam, a substantial contribution, it will be my dream. I think it will be the best thing. But I will try to offer this opportunity and maybe practice democracy if you will welcome it. But here is let's talk as colleagues rather than different sides of the barriers. The thermodynamics is a boring stuff, and I do not know how one can in modern world how one can publish academic paper purely on classical thermodynamics. So it's we need to be aware of it, but it is not something we can publish in Science and Nature, or at least JAX, with a because I'm assigned to teach and you are assigned to visit. I'll tell something about thermodynamics. But if we collectively decide that we need something more modern, I'll share my dreams and then offer if we all want to go a little beyond the rules and things. So the stuff that you got in the first part, quantum and statistical, is competitive. One can do research, publish, or at least make a little chapter to the thesis or a little approach, a little step towards it. And I have in mind a project that we can do as a team. And if we all contribute, it maybe can be a paper made with all attendees of the class at the end of the class. It will have marginal connection to thermodynamics. It will be a lot of connection to statistical and quantum. And I'll tell basically what is the project, and I will invest maybe 10 minutes each class about the project, and then doing boring stuff that I have to. So you did learn from Professor Brookhouse about partition functions, statistical sums, right? Like how to get and somehow to find density of states for different electronic systems, and how to combine these two concepts. For example, by merging together partition function and density of states for basically any quantum or classical system, one can go to observables, such as, for example, heat capacity, ability of system to absorb or reject energy. And you do know that there are several degrees of freedom, and they have different density of state, right? So there are translational, rotational, vibrational, and electronic. And if you focus on, first three have connections to classical theory, and electronic are completely novel, and human intuition sometimes fails. And in electronic, there are just transitions between electronic states, and there are things which are related to spin degree of freedom. And concept of spin is not new for you, right? You are doing nuclear magnetic resonance. So some of you are even serve or did serve as a facilitator of this equipment. So spins, either on nucleus or electrons, are degrees of freedom that can describe density of states of a system with spins, and can enter into partition function and give observables, such as, for example, heat capacity and some other. So the project that I have in mind, and we all can do, is heat capacity of spin lattice of magnetic material. And I know what I'm doing. I'm violating rules. Instead of thermodynamics, I'm just telling about a project. But I promise to finish in 5 minutes and go to standard thing. So the material is transition metal, ruthenium 3+, connected to 3 chlorines. But it is only a small. Do you see it online? Is it big enough? Yes? Okay. Yeah, thank you. And this is all, this thing is arranged in a periodic fashion. So there are another, how to say, unit cells which, so it forms a network of ruthenium and chlorine in a plane, in two-dimensional thing. So ruthenium 3+, through your inorganic chemistry expertise, how many paired or unpaired spins you can expect there, or where to look if you forget about it? Okay, okay. So if you have octahedral 2+, so for ruthenium 2+, and I like making errors, intentional or unintentional. So please watch me and correct. So I think in 2+ it is 6 uncompensated, 6 compensated electrons, right? If we do 3+, then we have 5 electrons, and only one of them is unpaired. So basically, this problem is a lattice where in the centers where rutheniums are, there are electrons which can be up or down. And these electrons can interact with each other and either help each other to be co-oriented or be less collegiate and prevent each other from cooperating and make antiferromagnetic. And this system can magnetize, like have a overall magnetization because of the cooperative states of the spin. And if we heat it up, they start disorient and lose this orientation. So when the system loses orientation, the amount of states that contribute to density of states and to statistical sum, to partition function, will become much more. So when they are all oriented, it's only one state, right? When they're disoriented, there are like millions in microscopic, or like, I do not want to count them, many. And statistically, it is much more probable. So if by thermal energy disoriented states are disordered, there are a lot of such states, and they're statistically preferred. So if one starts to heat such system, there should be a peak, a spike when we do have temperature, heat capacity. So it should be a peak when system goes from oriented to disoriented. And if you were speaking in the previous part about phase transitions, did you? Phase transitions, like evaporation, crystallization, melting. Oh, okay. Then we'll speak about it, and it will be legitimate. So you know, the like gas can condense into liquid, liquid can freeze into crystal, and it can go other ways. It's first order phase transition. And there are some additional phase transitions that are not seen by naked eye, but there are internal transformations. And such example of such transformation is change of magnetization of a material. And basically, similar thing you can observe if you buy a compass, like expensive in a tourist store, and then bake it in the oven. It will stop responding to magnetic field, and then your money will be waste. So it will go to disoriented or loss of magnetization. So it will be still piece of iron needle, but it will be not magnetized anyway. So physically it is the same, but there will be phase transition of the second order. And the idea for us as attempt, again, I will not do it without your votes, majority or vast majority or everyone, is to do some little exploration of this project. And I have some simple codes that one just need to click the button and run and explore how this basically heat capacity and magnetization for this material. Why? Because it is highly related to at least first part of your course, and second, it is something that there are several reasons. Something I hear here. I can. If you're not speaking, please try to mute the microphone. And you're welcome to give me a suggestion that I mute microphone so that we do not affect each other. So this problem that you as intellectual elite of the globe and after successful completion of the first 2 months of this class, you already understand all details and strategically what this problem is, and it doesn't seem too complicated, but it is a objective challenge for world science, and any motion in this direction is publishable. So it's not far from knowledge that you already have. Why? The main challenge, because it is two-dimensional, and the things are connected here not in the regular 90 degrees, but each ruthenium has 6 neighbors and 6 fluorines, but there are only 3 nearby neighbors for ruthenium. So I should draw it this way: ruthenium, ruthenium, ruthenium. So it's like a triangle lattice. And there are no pen and paper solutions, so it's only computational. And the third reason, there are smart words for models like this. We do not need it right now, but the name is Ising model. And if you follow popular science, you know there is an advent of quantum computers and competition between like Google, IBM, and there is a D-wave quantum computer. You may look. So it is a general quantum computer should replace regular and solve all problems, but by now D-wave or performs any human or computer in Sudoku game. But the principle of this quantum computer is based on the same math as one uses for this lattice of interacting spins. So if I'll keep telling stories and ask you if you're interested, but if you decide to, we can be not just completing the course, but put a foot in the door for competitive research. Okay, so I'm going to erase and chat a little bit about more about actual thermodynamics. And I'm quite confident that you all or most of you know this subject, and I will be just repeating it, and maybe you know more than I do, because my training was in physics, and I had thermodynamics basically on the undergraduate in 1991. And then as a part of graduate course that not a graduate upper level course that I didn't visit all meetings in 1994, and since then I didn't touch this material. Probably your knowledge is much fresher. So if we forget about partition functions, if we forget about quantum states, you know there are like ideal gas equation of state. There are thermodynamical potentials, derivatives, some heat capacity with constant pressure, constant volume, right? So you're aware of these things, and we need to revisit them. Just if someone watches recordings or connects, so that we can report that we do whatever we are assigned to do. So can you please help me and suggest what was the reason in human civilization to design such a branch of knowledge as thermodynamics? And do not hesitate.
To understand how matter behaves.
So John taught energy production, and Crystal?
To understand how matter behaves.
How matter behaves? Yes, how matter behaves is a quite global question to any materials, any natural science, right? And I like a suggestion of John how energy is generated. Do you have any other ideas or suggestions? Okay, I'll process from here. So, can our civilization work without thermodynamics? So, what cannot work without thermodynamics? If we are not scientists, if we are just regular people who just want to lay on couch, watch TV, eat food, when do we need? At which point we need thermodynamics? Not as at level of knowledge, but which devices that make our life more pleasant depend on knowledge of thermodynamics. Okay, so we cannot live in Florida without thermodynamics, and we cannot live in Alaska without thermodynamics. Okay, but okay, let's live in the pleasant climate. Can we live without thermodynamics?
Electronics?
Electronics, I'll give you an example. We mount solar cells everywhere, convert photons into electricity, and power our computers from there. There is no much thermodynamics. Or we put like Hoover dam, generator of the falling water, rotating alternator, and power our electric devices from there. It's possible to understand and engineer without thermodynamics. But you kind of feel that there is a trap in the question, that something will not work without it. So please try to give some examples.
Wouldn't your electronics overheat though, if we didn't understand like thermodynamics?
What, just once again?
Oh, wouldn't the electronics overheat if you didn't have an understanding of thermo though?
Okay. The electronics will fail after first 5 minutes of working without thermodynamics, but still it will work. So you'll have time to send a tweet message. But what will not work completely? Some bright examples. Like
your fridge. Your fridge.
Yeah,
fridge and freezer.
So I need to live on a farm and have a live cow for milk and live without fridge. But yeah, you're correct. But can I drive to the store without thermodynamics?
No, because you have combustion engines.
Exactly. So combustion engines, right? So combustion engines will not work without thermodynamics. And if we are not ready to sacrifice them, then we need to study this subject a little bit. So what else? You are thinking in a very right direction. Let's look into history. How the Egyptian pyramids were constructed. I know it is an open question, but how delivery of this building blocks was powered? Manpower, maybe horsepower, maybe camel power, right? But the muscles. Okay. And in medieval Europe, how the armor of knights was constructed?
Using a forge.
Right, with but still it was basically manpower, hammers, maybe combustion, which is not yet quite thermodynamics. But when went from medieval to industrial civilization, what was the main transition in the civilization?
They used coal power stuff.
Yes, coal and steam. Yes. And why? What is steam power? How does it work? Just we are coming to the answer, but what is the main principle? Turbines, but turbines are quite modern. What was before turbines? Between mills and turbines.
Wasn't that the combustion engine type thing? Because it's a little steam powered goes up and down thing. Little engines.
Exactly. Crystal, you are given a great hint. So does everyone understood what Crystal told? Yes. I see you understand. Can you just show it once again? It will be great. Do not hesitate. Okay. Yeah. Great. How can I pronounce your name?
My name is Paymon.
Paymon.
Yes.
Yeah. Nice meeting you, Paymon. So, he was right?
Yeah.
So she was showing that there is an assembly of four rods and pistons connected to crankshaft, and they rotated by alternating pushing, right? And okay, so I did translate what you were showing. Right. So expanding working media, typically gas, pushes piston and converts pressure into to power something useful for us, either electric generator or just lift coal from mines or whatever. So the engineering problem of to need to power some production of goods or just delivery of heavy things was a reason to design thermodynamics. So we are going back to the time of Industrial Revolution. And if you can design a steam engine without thermodynamics, it's okay, then we do not need it. And probably it is possible, but if you want to optimize it and make it economically efficient, to convert the energy of combustion of coal into mechanical power, then we may need some of the principles of thermodynamics. And all these differential equations, heat capacities, equation of states originate from there. So in some sense, thermodynamics is not science. It's applied engineering to design heat machines. And later on, like a couple centuries later, one did found that one can still consider it as science delivered in the courses, do completely theoretical thermodynamics without heat machines, but origin is there. And I'm trying to revisit it with you, or maybe behind you, because you know the things. But I may ask myself, like, where is the core part, or the center of this area of knowledge, and what are the marginal, like where to start from? And I think one should start from heat machines to be historical and logical organized. So let me check that I do not overuse your time. Okay, yeah, I still can go for. So, did you hear about Carnot Cycle, right? So you then you will not hear anything new from me. But I'm going to revise it. And before meeting you, I was briefly preparing, maybe a little less than I should. But if one goes into Wikipedia and looks for heat machine cycles, there are a dozen of them. And Carnot cycle is mostly stupid and useless. So it is, and the Wikipedia tells that it is not applied to any of the operational, functional, and efficient heat machines. So it's more like a abstract thing that one can briefly describe and introduce concepts. So by playing with Carnot cycle, we shouldn't expect much and tell, oh, I know Carnot cycle, I will be engineer of powerful turbines. No, it's just basic concepts. And I'm going to reproduce my vision of what is Carnot cycle, maybe slowly introduce some concepts, maybe asking your help at some steps, and then develop a little plan what we should do in the course, which concepts from real life we should wrap up into form of mathematical equations and later use for whatever advanced PChem science. So I'm going to draw at least 5 pictures. So if you are taking notes, also please assign time, place on your notebooks. And if you know Carnot cycle, you can even, I believe that I can ask any of you to go to the board and explain it. I just want to practice it because I never did it before. So there will be cycles that schematically demonstrate rod. It is soldered, like completely insulated on the bottom, and in the middle there is a piston. And on this piston we can put some heavy mass, like 1 kilogram or whatever. Okay. And there is a amount of volume. We can make it in our Gedanken experiment. We can make it transparent out of glass and just measure the amount of volume and put little ticks, same as you do in when you measure liquids. So we call initial volume, volume 1. So we measure amount of volume, and it is filled with some working media, which can be gas, it can be steam, it can be evaporated alcohol, it can be results of combustion, if it is internal combustion, like carbon dioxide. And so the goal of this machine, and it is insulated here, so there are no leaks, and the gas is pressurized. There is also pressure inside, and this pressure pushes this piston up, the mass pushes it down, and it is in equilibrium, right? So the goal of us as industrial revolutionaries who want to go from hammer blacksmith power to something that rotates and generates goods without help of human automatically. We want work. We want to power just lifting this heavy weight up. So instead of horsepower or main power, we just want to lift it up. Maybe it's like a piece of coal out of mine that we want to lift. Maybe we will connect it mechanically to a rotating crankshaft and power the train. It's not our question. We just need to focus on the working media inside. So we can put gunpowder inside, ignite it, and then it will be like a little cannon. it will deliver this mass higher up easily, right? What's wrong about powering our cars with gunpowder?
It's one and done.
One and done. Crystal, thank you much. Yes, one and done. So it's not economically feasible. So if we need to repeat it again and again, it's like, well, if one combines car and machine gun and counts on the returning force and just fire in one direction and moving into other, maybe it will work, but not very efficient and not very safe, right? So we need a procedure that will be repeating, right? And also we do not want to waste this gas. If it is steam, it is not very expensive, but still we do not want to create it over and over. We may want to make something that repeats in cycles. And the idea is not because it is most efficient or that people who designed it were like their mind were cycles on creating cycles. It is just a way to make things economically efficient. It is the same idea as we practice right now. Recycling and upcycling of polymers. There, 200 years ago, it was recycling and upcycling of steam. So it doesn't go away as much as possible. So yeah, if we put it on a stove, here is my attempt to draw fire, or put a thermostat with temperature 1, the gas will start expand, pressure will increase, and will push things up. But we need to design the procedure in such way that after it delivers, maybe then a human worker will take the mass or replace it with smaller mass, the mechanism will go down and then repeat things again without waste of the gas. So there should be heating and cooling, right? It sounds natural. And here I observe a little challenge that I didn't understood in high school and undergraduate things. Maybe you are well aware of it. So I need so write it heating, and then after it expands, so it is figure number 1, and I need total in 5 figures. And here I will do figure number 3. So after it has been lifted, piston has been lifted higher up, we still have some mass. We may put little crumbles of ice around, like ice bath, and cool it. Ice, and tell that it is temperature 2. Then it goes down, right? And then we cycle in heat and cool, so it should work. Something, but in the figure number 5, which is diagram of the Carnot cycle in the pressure and volume coordinates, right? You will see there will be curvy lines corresponding to transitions, up and down, changing simultaneously pressure and volume. And the idea is that we do complete cycle. So the system, the machine, arrives to the same condition after completing cycle where it was before in all aspects, including the pressure, volume, and temperature of the gas. But if we have constant temperature here or there, right, then the gas inside this machine will follow ideal gas state equation, right? And I'll probably practice re-deriving it just for myself, because I'm sure that you know both equation and its derivation. It's something that if any of us selects high school teacher career, is what one should do there. And I'll just practice today or next time. So if, and this figure I will redraw it again. Right now it is only sketch. So if one practices ideal gas equation of state, it shows that pressure is inversely proportional to the volume, right? And we will have a family of lines which are parallel to each other. So there is, and on one hand. On another hand, we need to form a cycle. We need to come to the same point. So family of parallel lines will not be able to complete the cycle, to feel a curve that will look like a loop, right? So the ideal gas equation of state is not enough. So if we believe only in ideal gas equation of state, our heat machine will either not work or will not work on a continuous way, or it will give insufficient power. So there are processes that are missed in this attempt to model and understand what is going on. So and this little idea will drive a little derivation and of a new equation that is similar to equation of state, but it is like a next step. So and my plan is to fill number 2 and number 4 and add some additional lines and redo the number 5. So can you help me and guess, maybe from your previous knowledge or from your intuition, what is missing? And it's not a big challenge. Without any preliminary knowledge, one can guess and way to go just naturally. Please try. So which process is missing? Which process is not shown? Basically, what should I? What is between these two processes? Yes. Yes, connect these two lines. I agree. So he is very correct. But this is empirical and heuristic approach. If you want to be a little bit more microscopic and describe how do we connect these lines, what it will correspond on our intuitive interpretation. So here we heat it and it lifts, it elevates the mass. Here we cool it down and it goes down. So the mass basically compresses the piston and the gas. What is in between? Just let's think for maybe 30 seconds.
The transitions?
Yes, transitions. And a little bit more details.
Like the process of it going up and the process of it coming down, because you got it down getting heated, so it's going to expand. So wouldn't it be the expansion and then the contraction?
So yes, but if we want to be meticulous and rigorous with words, then for contraction and expansion there is one word missing. There is one word.
Adiabatic?
Yes, perfect. So can you teach me what it is? What is adiabatic expansion or adiabatic contraction?
Where the temperature stays, isn't that where the temperature stays constant?
No, when
no.
Temperature stays constant, it is either thermic. It is when we put heat bath or ice bath, right? And so it is isothermic, corresponding to ideal gas equation of state. But what Crystal very correctly suggested, the adiabatic expansion is an additional process. So let me give an example. Suppose I have forgotten to fuel my car and I'm missing to arrive to the lecture in time. And I want to drive bike. But the tires are flat. So I'm trying to pump it. So when I'm pumping, and then check the temperature. Will the temperature stay the same or change when you pump? Yes. So we can consider a process when compression or expansion simultaneously changes the temperature of gas inside. Okay, so this is a key, and this is what you were supposing to add here. So we need a line that will have different curvature than ideal gas. So it will look also like a hyperbolic, but with different power. So it will be like P to the power 1 over V to some power. So we need to add these processes, and these processes correspond when compression and expansion is associated with gradual change of the temperature, because when you compress the gas, you increase its internal energy, you speed up its molecules, right, and temperature raises. So the correct word here for these fat lines will be adiabatic compression or expansion. Compression or expansion. Okay. So how do I draw it? It was the main challenge for me last night, how to draw in a graphical form the adiabatic expansion. And I'm just looking if you have anything except black. No. You have only 50 shades of black. So I'm redrawing a piston. I'm putting the volume somewhere in between these two things. And so maybe I put it V2 volume inside. And now it is where I would like to use different color, but maybe I will use just the dashes. So a lot of you do NMR experiment and you cool down the facility with liquid nitrogen. And liquid nitrogen is transported in which containers? Dewars. Or if one wants to bring hot or cold food, one use thermos, which is also dewar, right? Which insulates, prevents heat transfer. So suppose I put a little, I'm not a good drawer, but suppose so heat insulation, a little dewar or insulating blanket, as one puts if person accidentally may cool down, like aluminum foil. So blanket, dewar, in heat insulation. So after we heat it up, we stop heating and close heat machine into a dewar, into heat insulation, and just follow what is going on. So heat is not transferred to the system anymore, but it's still quite warmed up. It's quite high pressure. So it keeps pushing the this mass out, right? It keeps expanding the volume, and then pressure decreases. But at the same time, because energy of kinetic motion of molecules is converted into this motion of the piston up, the temperature decreases. So temperature goes from T1 to T2, decreases. And it is because the heat machine is enclosed in a dewar. Okay? Whew. Basically, that's it. I'll continue, and we still have about 2 months of a course in front, but this is a key part for the subject of thermodynamics. So equation of state is not sufficient. We need another process, which so here is number 1, here is number 2, and at this line we are heating. Here we stop heating, and it is keeps increasing the volume from volume 2, let's say, to volume 3, and it drastically drops the pressure. And at the same time, there is no heat transfer between system and environment and external world. So the temperature goes to T1 to T2. So it is adiabatic expansion. Okay, and then did you hear about demon of Maxwell? So suppose, can you tell who is demon of Maxwell?
Well,
A little interview.
vaguely, I remember that Maxwell's demon will either only allow or not allow a certain energy into a box.
Okay, yeah, correct. Thank you. So it is one of the hypothetical principles of perpetual mobile. So there, if Maxwell's demon exists, then one could generate energy for free, basically, to move energy from cold chamber to hot chamber, which is unnatural. Here, I mention it because we assume without looking into specifics that the machine is tuned that as soon as it reaches cool temperature T2, maybe temperature of freezing or something like that, we immediately remove this dior and place it on the ice bath. So we stabilize temperature. So it is thermostat, right? Like cool stove, a stove that not heats but cools. And let's look what will happen here. So we expect that it will start cooling down, but temperature will stay the same. But since the energy can be released from the heat machine into this cool bath, it will start. The piston will start moving back. So basically, this mass will compress. Will be allowed to compress. Before it was in equilibrium with pressure created by thermal motion of molecules, and now since energy of thermal motion of molecules is allowed to dissipate, the piston will slowly start moving back, and the volume will start decreasing. So the piston will go down, and pressure, although we move down, the pressure will increase. Okay? So so it will move onto certain stage that we'll call maybe somewhere here, like V3. And then there is a last stage that we are going to take this system where piston has already compressed the gas, and now we are going to enclose it in dior once again. So I will draw the dior. And draw this rod and piston. And And let's think what will happen. So the heat is not released from the system anymore. We have the mass performs mechanical work. It's like me preparing bike to ride to the lecture. So by compressing, it increases internal energy, increase heat energy of molecules that start moving quicker, and it makes several things. It contracts the volume, it increases pressure, and it increases the temperature. So it will be adiabatic compression. Adiabatic compression. So we still go down, but temperature goes from T2 back to T1. It heats up. So we isolate it, but inside it heats up naturally. Because mechanical work is converted into quicker motion of molecules. And this, so this was cooling. And now we consider from number 4 to number 1. So this fat arrow. So it is adiabatic compression or adiabatic heating. And because the curvatures, and we will need to derive equations for these curvatures, which will be different from ideal gas state, because they are different, we can form closed loop cycle. So basically, if I need to serve to operate this machine, my service is follow: put hot stove, wrap it in blanket, remove blanket, put on a ice bath, wrap it in blanket, put back on a hot stove, and repeat. And then the gas will be not wasted, and the rod and piston will move in respect to each other. So it will be a repeating pattern of motion that may drive, give some power to develop. So the goal for the next operation is maybe check if yeah, I think if you finish about now, no one will object, right? You're not as hungry for knowledge to stay for the day long. So the goal for our next meeting to start, we will start from repeating ideal gas equation, and then getting adiabatic, and then looking on this curve from the point of view of more mathematical. And then from there, we will see what else is needed to make the machine more efficient or to make our knowledge more profound. If you need some additional concepts, if you can introduce their heat capacity, if one can compute the efficiency of the heat engine. But I think it is enough for today. Everyone is welcome to disconnect or depart. I'll stay here to answer any questions. Please.
So number 4 is adiabatic compression. Then I think number 2 is adiabatic expansion. Then what is the number 1 and number 3?
Isothermic compression and isothermic expansion and isothermic compression. Yes. I think it was mentioned in the general syllabus, but I can quickly compose one. And I really want to maybe when next week is break, right? Good. So maybe so when we meet on Wednesday, I want to maybe practice a little democracy or collect your opinions if we need to do only boring thermodynamics or we want to invest a little time in project. And based on your opinion, I can tailor the syllabus and plan so that, okay? Just think and develop your opinions. I'm good either way. So it's free will. Like if you go only boring thermodynamics, maybe then I need to design some exam and problem. If you go into project, then maybe it will be enough for overall grade. But we'll do things collectively so that everyone is happy.
For the project, are you going to give us guidelines? Because I got to admit, the statistical thermodynamics I still suck at.
Please repeat.
Are you going to give guidance on like the project guidelines for if we do the project? Because I got to admit, I'm not that great at statistical thermodynamics yet.
Well, I will still give all material related to thermodynamics so that
no, not for the project. Will you give us guidance on how to do it?
Oh, guidelines.
Like guidance, like
yeah. Of course. Yes, I'm interested in the success of the project, and with your permission, even if you as a team will do work, I will write myself as a co-author of this possible future paper, and I will get piece of your glory to myself. So yes, and I did some preliminary steps that I will share so that we can either probably just contribute, different parts of members of the team contribute a little bit, and I have a plan, but please think about it and we'll discuss it on Wednesday so that it will be not no pressure from my side, no pressure from your side. You just think and develop what is more comfortable and matching your life goals.
Sounds good.